Hi and welcome. This tutorial will be dedicated to geometric nonlinear analysis in unbraced 3D, and we're going to follow up on a bridge that was previously modeled and run in another tutorial. This is the curved plate girder bridge, three girders. And so here the difference is that instead of running an eigenvalue buckling analysis, we're going to run a large displacement analysis. So large displacement analysis is really the same as geometric nonlinear analysis. Okay, so we won't go through the modeling process again. You can look at another tutorial for that. Instead, we're just going to go to this form here, the large displacement analysis form. And so we have one stage for which we are going to perform a large displacement analysis. We are going to track 2 degrees of freedom, and here the idea behind tracking degrees of freedom is that we want to plot load versus displacement curves for specific displacement. So here we're tracking girder line 3, a node at 50 feet from the start, from the first abutment. So that's really at mid-span because the girder in question is 100 foot long. Location on the cross section is 8 and 2, so we are tracking the top flange node and the bottom flange node, and direction 1, which is the global X direction. Okay, it's the global X direction, so the transverse direction, or the lateral direction, if you will. General recommendations, I'm going to read them out loud because I think it's really important. You need to perform a first order analysis first. You need to have a pretty high number of load increments. This is to help the solver have a reasonably large tolerance on the residual load vector. So here we're going to use 0.01, which is quite tight. You don't want to use 0.0001 or something like this. There's 2 options here. Either automatically update the load increments. That's in case you have pretty fast convergence at the start, so you want to take big jumps in terms of load increments. But here we're going to apply equally spaced load increments with 10 load increments. So we're going to apply 0.1 times the load, and then 0.2 times the load, etc., etc. We are going to update the stiffness matrix at each load increment. This is another way of saying we're going to use the modified Newton-Raphson method. And we also have the option here to specify a minimum and maximum number of iterations per load increment. So let's say at least 5. So that means that even if we get under the tolerance, we'll still run 5 iterations. It can be 1. Okay, this doesn't really matter, but let's say it's 5 and 100 here, meaning after 100 iterations, if the solver hasn't found a state of equilibrium, in other words, if the solver hasn't converged, or in other words, yet if the residual load vector, its norm is still above 0.01, then we'll get an error message saying that, hey, sorry, but we can't find a state of equilibrium. In that case, that would mean that either there is no state of equilibrium and we are really past the buckling load, and that's the most likely issue, or you need maybe to update here, refine your parameters, maybe increase the number of load increments. So let's run the analysis here. So you see we're applying the load in 0.1 increments. It's going pretty fast because the bridge has only about 40,000 degrees of freedom here, so it will take about a minute. And if you look carefully, you'll see that you gradually need more and more iterations at each load increment. That's because the nonlinear effects are starting to kick in as the load is being applied. So you see here for the last load increment, we needed 25 iterations. Let's extend this, go to another view. Let's zoom in. Let's not show the load or the axis. Let's move up a little bit and move left a little bit. All right. So the linear elastic solution gives us a maximum displacement of 5.7 inch. Okay, which is happening about here. The large displacement analysis is giving us, let's see, this is the first increment, load increment number 1. Let's go to 2, load increment number 2. How many load increments do we have? We have 10, right? Load increment number 10 over 10 out of 10, meaning we have applied 100% of the load. And you see here, the maximum displacement is equal to about 8.9 inch, which is fairly higher than a 5.7. It's about 20% higher. And just the shape itself of the displacement is different. You can see that girder number 1 here is really fully engaging and is going along with the other two, which is kind of something we saw in the buckled shape, you know, that mode we've seen, the second mode before in a previous tutorial. A way to look at this is to go to the charts here and output both the first order and second order charts at the same time. And you see that for girder 3, in the Z direction, the vertical direction, for this node, for node number 2, we have an increase in the displacements of about, I don't know, 5%. If we go to the component 1, so the lateral component, or the X component, and if we go to, say, node number 8, let's see what we got. We got something much higher. We can see that the lateral component of the displacement vector is by, I don't know, 8 times higher here. This is really the benefits of the second order analysis. We can really capture the out of plane displacements much better. So again, the large displacement analysis is about finding a state of equilibrium on the displaced shape, on the deflected shape of the structure. We can look at the layovers as well. The layovers are the relative displacements between the top flange and the bottom flange. And let's output both the first order and second order analysis. And you can see here the bottom flange is also deflecting more with the second order. So here the increase is about, this is 25%. So here it will be about 12% or 15%. Okay. You can also look at the cross-frame forces. This button here means, this radio button means the cross-frame forces from the linear elastic analysis. So as seen in a previous tutorial, the maximum forces are about plus 18 kips in tension and minus 18 kips in compression. Same here, that's for these two cross-frames, as expected. If we look at the cross-frame forces obtained on the deflected shape, so with a large displacement analysis, these forces increase by about 10%. Now we had 18, we have 22.5. So actually it's about 20%, right? It's about 20%. Correct, yeah. So, and final thing, just click on this button, which is available only if you run a large displacement analysis. These are the true degrees of freedom that we are tracking here, okay? Degree of freedom 1 in blue is the X displacement of node number 8, so the top flange node at 50 foot along girder 3, so that's midspan. And degree of freedom number 2 in red is the bottom flange. And you can see that initially the bottom flange is having a negative displacement, so it's going to the left, and really X being negative. And and the top flange is going to the right. But as the load is increased, then the system, the bridge as a system deflects laterally, and even degree of freedom number 2, which is the bottom flange, deflects to the right together with degree of freedom number 1, which is the top flange. So I hope this tutorial was really useful. This is something which you can apply on your steel structure during erection to check, to look at really what would my displacements be if I were to run a second order analysis. Typically you would expect a 10% increase. Here we've got about a 20% increase. That's because we've got a pretty flexible system with 5.7 inch already, just using the first order analysis. Stay tuned for other tutorials.